In this video, we're going to introduce the concept of operators. This is something you're going to get very familiar with as you go on in quantum mechanics. The first step is to discuss the so-called position operator. We're going to define the position operator. The second is to derive the momentum operator. And then we'll talk about the uncertainty principle that relates these two operators. Suppose we have many systems, all prepared in the same way and all a state described by a wave function, psi of x and t. So this is the one way to look at this probabilistic or statistical interpretation of the wave function, is to start thinking about the fact that you have many systems. You prepare them all the same way, then you measure them all, and that gives you a statistical distribution. And that should then relate to the calculation you can do using quantum mechanics. So we have all these operators, all these systems prepared in the same way, all in a state described by the wave function psi of x and t. Now, if we measure the position of the particle in each of these identical systems, we're going to obtain a result consistent with the expectation value, just as I said, of the position x, which we know how to compute because we already talked about how to compute an expectation value of some quantity of some function, and that is that the expectation value of x is the integral of x times the probability distribution dx. And we integrate this over all space. Well, that's easy to write. We can break this up into the two parts that we had before, that is psi star psi. And x is not a derivative, so it can move around freely between the two. And we're going to put the x in the middle. So what we have then is the expectation value of x can be written as the integral of psi star x psi dx. So in this arrangement, this is sort of the formal location where you put an operator. The operator x, in this case, acts to the right on a wave function. And you'll see later how we use this formalism. It makes a lot more sense when we're talking about operators that aren't just variables. In this case, the operator is a variable. So eventually, we're going to get to something called the bracket notation, which we use in quantum mechanics, and it allows us to do a shorthand notation for these, what could be very lengthy and long written out integrals, and allows you to write quantum mechanics in a shorthand that is understood to be all made about integrals. But it also gives you the opportunity to go beyond normal space and write down wave functions that have nothing to do with variables like x and y and t. So if we know how to calculate the expectation value of x, then what you expect over time, because remember the wave function is a function of time, that expectation value should change. And we can sort of imagine that that's a velocity of some kind. It's the velocity of the expectation value. And we can write that velocity and calculate it as the derivative d by dt of the expectation value of x. Remember, the expectation value of x still has time dependence. And so when we put that together, we then have the integral with respect to x, minus infinity to infinity, and then we have x d by dt. We can pull the derivative into the integral, right, and it becomes a partial. And x doesn't depend on time, so you pull it through the integral, and now you have the integral, pull it through the derivative, and you have the derivative applied to psi star psi. But we just did that in the previous video when we were talking about the normalization integral. So we know what that becomes. That is very simple. We don't have to do that again. We can write down that this then becomes IH bar over 2m, partial with respect to x, of this quantity here, psi star partial psi with respect to x, minus partial psi star with respect to x times psi. And these two terms here, with the partial with respect to x, are simply this quantity here, the partial with respect to time of psi star psi. And then you also have an x in here. Well, we can solve this integral, or simplify it at least, by applying integration by parts. So I'm going to choose u as in red here, which is the x, and dv is all the blue stuff. And remember, when you do integration by parts, you're going to see this a lot over the course, is you take uv minus integral of v du. Well, when we integrate dv, clearly we integrate this stuff, we get what's in the brackets. And so when we take the derivative of u, we get 1. So we get two terms. uv, which is ih bar over 2m times x, times the quantity in brackets, evaluated from minus infinity to infinity, minus the integral of v du. So that, again, has the ih bar over 2m. And then you have integral with respect to x. But now we've taken the derivative of u is just dx, because x, derivative of x is dx. Sorry, not 1. It's 1 times dx. And so you have a dx here, which is the du. And you have the v here. And now you have to do this integral here. Well, this term here goes to 0 for the reasons we talked about before, that the wave functions are well behaved at infinity. And so while this goes to, x can go to infinity, these must go to infinity rapidly, and everything's well behaved, and these will cancel out. So what you're left with is this term here, minus ih bar over 2m, and then you have this quantity in parentheses psi star partial psi with respect to x minus partial psi star with respect to x psi dx. Well, we can integrate the second term by parts again. We leave the first term alone, but we integrate the second term by parts. And now we choose partial of psi star with respect to x dx. And then psi is u. Well, clearly what you get now is, again, two terms. And the two terms, three terms actually. The first term is the unchanged term here. Again, you have minus ih bar over 2m out front. You have this integral here, which we're going to leave alone for the moment. Then we have minus uv evaluated at the endpoints. But the integral of partial of psi star partial x dx is just psi star. So this becomes psi star psi evaluated at minus infinity to infinity. This is going to go to 0 because the functions are well behaved. And then you have v du. And v du, clearly here, when we take the derivative, we're going to get partial psi with respect to x dx, and that's du. And so now we're left with an integral psi star partial psi with respect to x dx. But if you look at that, that's exactly this term here. So this term goes away, and this term is doubled up, and we're left with minus ih bar over m, integral psi star partial of psi with respect to x dx. And so this is the derivative, the time derivative of the expectation value of the position. It's a sort of velocity. Well, I reproduced that result here. We have this result for the time derivative of the expectation value of position, and we're going to assume that this is related to the expectation value of the velocity. And therefore, we can see how to compute the expectation value of the momentum. So if we assume that the derivative of the expectation value with respect to time of x with respect to time is equal to the expectation value of the velocity, and that's called Ehrenfest's relation, which we'll prove in one of the problems in the book. You can then rewrite this as a momentum, remembering that p is equal to mv for non-relativistic systems. And so we have to take v times m to get p, but remember there's an m in the denominator here, so that cancels out, and we're left with minus IH bar integral psi star partial with respect of psi with respect to x dx. And so what we now have is the expectation value of p, the momentum. But p is an operator, right? This is the momentum operator. So now looking at this, I can see how I can make this into a momentum. I can write down what the momentum operator is, because if you remember, the formal way to put the operator is in between the psi star and the psi. So let me move that IH bar in and group this properly. And we see that we can write this like integral of psi star times the quantity minus IH bar partial with respect to x psi dx. And we can see that this is now an operator which acts to the right and gives you the momentum, the expectation value of the momentum when you integrate. This must be the momentum operator. So we now have two operators that we've written down, and we're going to write them in a particular way right now, and we'll write them differently later on according to what the text writes. So the operator x is just x. There's some ambiguity there about whether it's a variable or an operator. It's the same thing. But the operator for momentum is minus IH bar partial with respect to x. So we can now write the expectation values of position momentum using the operator formalism. Partial with the expectation value of x is just psi star x psi dx. And the expectation value of p is exactly what we had on the previous page. Now, as you know from classical mechanics, all other dynamic variables besides x and p can be constructed using position and momentum. They're just functions of position and momentum. Therefore, as in classical mechanics and quantum mechanics, we can develop operators for all other dynamic variables by just making up the appropriate functions with respect the functions of x and p. For example, the kinetic energy operator is p squared over 2m. So the expectation value of the kinetic energy is just the expectation value of p squared over 2m. And this we can write as integral of psi star minus h bar squared over 2m, right? So you now have the 2m coming in from here. You get minus I times minus I gives you a minus sign. And you have h bar squared on the top, and you have the second partial with respect to x times psi dx. And now if you look at this, you realize this is the first term on the right side of the Schrödinger equation. And that's why we said at the very beginning that the Schrödinger equation could be written as a conservation of energy form, where the kinetic energy is that first term. And in fact, that is the kinetic energy. In general, then, we can write any quantity or any operator q, which is a function of x and p. We can write its expectation value by taking an integral, putting the q, which is a function of x operator, and minus IH bar partial with respect to x p operator. It's the same function as x and p. And then put psi and dx, and you integrate it from minus infinity to infinity, and we now have the expectation value for some arbitrary operator that's a function of x and p. So if you accept that a particle has a wave nature, and that can be described as a normalized wave function, we can now ask what the wavelength is of that particle, and what the particle position is, right? Because we can measure the wavelength as something that's related to momentum. A wave number is similar to momentum. And we can measure the position of the particle by taking the expectation value of the position. So let's imagine that we have two cases for the wave function. The first wave function has extended oscillations. So this is a well-defined wave function. It has a well-defined wavelength. In other words, if you look at that, you can tell me what the wavelength is. And it goes to 0 at infinity. It's nice. But you can't tell me very well where the position is, because if you take the square of this, the probability density, yes, does oscillate a little bit, but it's pretty much flat wherever there's a peak, either positive or negative peak. So that's going to be equally spaced. It's not going to have a well-defined position. The other case would be having a pulse-like wave function. Again, this is well behaved because it goes to 0 and infinity. But now the position is well defined, but I couldn't tell you what a wavelength of this is. In fact, if I asked you what a wavelength is, you wouldn't be able to tell me because there's no oscillatory behavior that can give you an idea of what a wavelength is. The wavelength, of course, is directly related to the momentum by the de Broglie relation. The de Broglie relation, remember, is P is equal to h over lambda, or 2 pi h bar over lambda. And so if I know the momentum, the expectation value of the momentum, I can calculate the wavelength. This is basically the same as the wave number times the factor of c. Therefore, what you've clearly heard about before is the Heisenberg uncertainty principle. We'll get to that in more detail later on and really actually prove a generalized uncertainty principle. But the Heisenberg uncertainty principle, we know what it is. We've all heard it, and that is that the standard deviation of x and the standard deviation of p, if you multiply them together, they're bigger than or equal to h bar over 2. And what this says in words is that if I know the position of the particle well, I don't know its momentum. That is, I don't know its wavelength. If I know the wavelength of the particle well, I don't know its position. And that's really all the uncertainty principle is. And there's a reason why these two variables are related that way. It's because they have a property that they do not commute with each other. And we'll get to commutation relation a little bit later.